Hello and good morning to all participants around the world. And thank you for joining the third edition of our online webinar series, Hobby Topics. We would like to welcome you to today's presentation about our ethanolic extract, the so-called Total Resin Extract. My name is Frank Pfeiffer and I'm the Technical Director here at Hopsteiner in Germany. I'm guessing you have all become familiar with webinars over the past few months. So I just like to say a very brief word about our setup that we have. The webinar is scheduled for a total 1 hour, starting with a 40-minute presentation, followed by a Q&A session. During the webinar, both your microphone and your camera will remain off. You can ask questions or make comments at any time via the Q&A tab in the webinar menu. The questions are directed to me and will be taken up at the end of the presentation. So here with us today is Dr. Martin Biendl, our Head of Research and Development and Analytics at the German branch of Hopsteiner Group. Martin received his PhD in organic chemistry from the University of Regensburg in 1990. His research experience covers the needs of hops for the brewing industry and beyond. He is a representative of the International Hop Industry Corporation in the EBC Analysis Committee and since 2001, chairman of the Hops Subcommittee. As the EBC representative, he is also co-chairman of the International Hop Standards Committee. In 2007, he was elected to the board of the German Hop Trade Association. In addition to numerous publications in international brewing journals, he is also co-author of 2 books covering the full range of hops. Let me say he is a hop expert. So Martin, it's your turn now with your presentation, and all people on the screen have fun.
Thank you, Frank, for your introduction. Also from my side, welcome to everybody around the world. Welcome to our today webinar presentation on the Total Resin Extract. And I would like to give you deeper insights in this hop product from A to X. Before we start with the alphabet, I would like to give you some general informations. You all are aware and know that the most important ingredients of hop cones, and here I talk about dried hop cones, so the product delivered from the farmer, and fresh hop cones. And the most important fraction present in these cones, mainly in the lupulin glands of the cone, are the bitter resins. Dependent on the variety, we have a range of about 10 to 30%. And the main part are the soft resins, and the most well-known compounds are the alpha and beta acids. Beside of soft resins, also the hard resins belong to this fraction. And it became known during the past few years that the hard resins of fresh cones are not consisting of any deterioration products of alpha or beta acids, but they show another group of compounds more from the polyphenolic range, and xanthohumol is the main compound in every hard resin fraction. Beside of the bitter resins, we also have the essential oil in the yellow lupulin glands of the hop cone. The range, depending on the variety, is about 0.5 to 4%. And there are 2 groups, more the non-polar components, like terpenes, like myrcene, for example, and there is a group of more polar components, and the most well-known representative is Linoleal, a terpene alcohol. Beside of resins and essential oil, the hop cone also shows polyphenols. Depending on the variety, the range is from about 3 to 7%. And these polyphenols are consisting again of various groups. And the first group are the prenylflavonoids. Main representative is xanthohumol, and you can see here that there is an overlap between hard resins and polyphenols, because xanthohumol is a polyphenol, but it is contained in the hard resin fraction of the hop cone, and it is part of the lupulin glands. The same is true for the polyphenols bound to glycosides. This can be various flavonols or multifitols. They are either in the lupulin glands or in the leaves of the hop cone. And the flavanols, also called tannins, they are only contained in the leaves of the hop cone, and they are the main part of the polyphenolic fraction of the hop cone, and they consist of monomers, catechin and epicatechin. And these monomers can build dimers, oligomers, or polymers. And altogether, these are the flavanols, the tannin fraction of hops. For beer bitterness, we have different types of hop products, and I would like to give you a short overview what we have. We have two types of pellets. Type 90, it's the most similar hop product to hop cones, because you only have some drying processes and some non-hoppy material are separated during the pelleting process, and so usually have a weight yield of at least 90%. And we have the so-called pellets type 45, and what you do here is you remove the leaf fraction of the hop cones, consisting mainly of the tannins, and you then have a concentration in the process. You have, for example, a weight yield of only 45%. So this is the reason why this product is called type 45. So actually you can also get different weight yields, type 60 or type 70. This is also then a concentrated hop pellet. And the difference to the type 90 is that you have a reduction of the leaf fraction. And then we have the extracts. We have two types of extracts, the Total Resin Extract, which we are talking about today, and the CO2 extract. And here in the extracts, you mainly have the bitter resins and the essential oil, and not the tannin fraction. And first step in hop processing is then that you isolate certain compounds from a hop extract. Then you get the so-called downstream products. And these downstream products then are only consisting of single bitter compounds, isoalpha acids, or there is the possibility to do a hydrogenation, a reduction of the double bonds or of the ketone group, and so actually you get the reduced isoalpha acids as pure compounds, either as row extract, as tetrahydroisoalpha acid extract, or as hexahydroisoalpha extract. So this is the range of various hop products that are available for bittering beer. And it's also worth to have a look on the development of hop products, because already 150 years ago, the first patents were published for hop extraction. At that time, steam or alcohols mixed with other solvents were used as extraction solvents. Steam is not the ideal solvent because water is very polar, but this was the beginning of hop extraction already 150 years ago. And 100 years later, and that's also very interesting, there were the first patents for compression of milled hop powder to pellets. So the history of hop extraction is longer than the history of pellet production, actually. And around the same time, the first industrial production of liquid isomerized hop extracts were done. And regarding hop extraction, in Germany, methylene chloride was the solvent of choice. And this methylene chloride had a good polarity with regard to extracting bitter acids and essential oil. It has a low boiling point. It's not flammable, so it's a suitable solvent, but it has some toxicological concerns, and therefore it disappeared fully from 1980 on. And the hop industry was able to develop processes based on two solvents actually contained in beer. One is CO2, and in 1979, the first industrial hop extraction with liquid CO2 was done in England. And liquid CO2 means that the gas CO2 is compressed to a liquid, and the temperature range is 5 to 15 degrees, and the pressure range is 60 to 65 bar. And only 1 year later, there was the first industrial hop extraction with supercritical CO2. And you get the supercritical CO2 after you have liquid CO2 if you raise the temperature and raise the pressure. At that time, the usual conditions for hop extraction with CO2 were between 40 and 60 degrees and 200 and 250 bar. And 1 year later, there was a patent application about the production of total resin extract using alcohol water as solvents. So this is the product we are reporting on today. And you see in this case, alcohol and water, also ingredients of beer, were then the extraction solvents. Then many years, nothing happened, but only last year, there was the first industrial hop extraction introduced using now supercritical CO2 at 500 bar. And I will come back to this version later on in the discussions. And I have a very simple slide now showing you the principle of producing the total resin extract, which is also called alcohol extract. Starting materials are hop cones, and then these hop cones are filled in an extractor. This is a countercurrent process, and so the extraction is done like you cook coffee in the morning. You fill in some hop or coffee powder, and then the extraction solvent percolates through the materials, and in the end you get a solution of extracted compounds. And this solution is then in our case evaporated, and this evaporation is done under vacuum. And after all the alcohol is removed, you can centrifuge the extract into two phases, into the polar phase, which is also called tannin extract. It's more the water soluble phase. And the other product is the non-polar phase. This is the total resin extract. With the alcohol water removed during evaporation, the problem is that because hops, even dried hop cones, contain 10% of water, you always make a dilution of the extraction solvent. So alcohol is diluted with water, and this alcohol water mixture has to be rectificated to achieve a constant concentration of 90% alcohol actually during the whole extraction process. And now I start with the alphabet. ABC, the first letters describing the total resin extract. So A is very simple, as you already learned. Extraction solvent is alcohol, also called ethanol. And this alcohol is coming from fermentation processes, so it's a fully natural solvent. B, bitter acids from the hops are extracted in a yield of at least 90%. And this is the overall process goal for hop extraction, either for CO2 or for hop extraction with alcohol. In principle, you could get higher yields, but then the extraction takes longer and it's less economically efficient. So usually the 95% extraction yield is the goal. Now we come to C, and for C, I decided for giving the chlorophyll as the word for it, because chlorophyll is extracted in the total resin extract as well. And therefore, the total resin extract has a bright, dark green appearance. And this is shown in this picture. Here you have the comparison between the total resin extract and different types of CO2 extract. Actually, one CO2 extract was produced at 250 bar and the other one at 180 bar. And you see a strong influence on the color. And this is because more chlorophyll, which is better extracted at higher at higher pressures, and it's fully extracted with the total resin extraction process. Okay, maybe it looks more like black, but believe me, it's dark green. It's a nice color that you see in this type of extract. The next letter is D, and for D, I would like to discuss the difference to CO2 extract. As we already learned in the beginning, these are the different fractions contained in the hop cone. This is not a relative scale, but an absolute scale. So you have 100% essential oil, alpha acids, beta acids, unspecific soft resins, hard resins, and tannins in the hop cone. And then when you make hop products, you have the pellet type 90. As I told before, it's most similar to hop products. You have all the tannins, all the hard resins, all the unspecified soft resins, and the beta and the alpha acids in these pellets. Only the essential oil is reduced to a low extent because during secondary drying processing or during pelleting, you have losses of highly volatile, some part of the highly volatile compounds. With pellet type 45, it's the same, but as I already explained in the beginning, you remove part of the tannins by separating the leaf fraction. And all the other fractions are identical to pellet type 90. And now the total resin extract. You fully remove the tannins. They are in the tannin extract, not in the total resin extract. And you have almost all the hard resins in it, close to 100% of the hard resins and all the soft resins. With regard to essential oil, you have some further losses. I come back to this later. And CO2 extract here in comparison to total resin extract, you see if you have some hard resins, it's only in traces, depending on the pressure for extraction. You have even some losses of unspecified soft resins, especially if liquid CO2 extraction is done. You have, of course, the alpha and the beta acids. And of course, because pellets are the starting material for producing CO2 extract, you have the losses that you have earlier in the processing to pellets, you have also in the CO2 extract finally. So this was the D, and now we come to the E. Under this letter, I would like to explain the extraction parameters for producing the total resin extract. As I told you, the starting material are hop cones, so that there is no pelletization necessary prior to production of total resin extract. This is also a difference to CO2 extraction. The extraction time is, depending on variety, 60 to 80 minutes, and it's a fully continuous process, whereas the CO2 extraction is more a batch or a semi-batch process. The extraction temperature is about 55 degrees, and the evaporation is done under vacuum, and it's a 4-step vacuum distillation unit, and the maximum temperature in the very first stage of this 4-step process is 78 degrees, but the whole evaporation only takes a few seconds or a few minutes, so the temperature load on the extract is very, very low. And maybe also interesting, because during this evaporation, all the alcohol is practically removed from total resin extract. So total resin extract, also called alcohol extract, is actually free in alcohol. F stands for filling station. So this is a picture of a filling station for hop extracts. And after homogenization of the extract at 50 degrees, the extract is filled in different tins and so on. And what you see here in this picture, therefore I selected it, you see in the back some vessels, and in these vessels the homogenization of extract is done, and you can homogenize batches up to 12 tons actually and fill them. So this is one big advantage also of hop extraction, because finally you have big batches completely homogenized. And so homogenizing is done at 50 degrees, and then filling is done. And we do filling either in tins from 0.5 to 4 kilogram, or drums up to 200 kilogram, or in containers of up to 1000 kilogram. And filling for hop extract is done either according to kilogram extract weight, so for example exactly 1 kilogram in a tin, or according to the alpha acids content, for example 500 gram alpha acids in one tin. And after homogenization you can do an analysis, and based on this analysis result, then you do the filling. Actually, this picture that I show you here is not an actual one, because we did some modernization in 2020, but I selected it because you see this homogenization tanks in the back. Now our filling station looks like that. So it was completely modernized last year, and more automatic processes are now going on there. G stands for glycosides. And these glycosides are contained in the hop cone. And the glycosides, these are substances that are bound to a sugar molecule. And these compounds are only transferred into the total resin extract, but not into the CO2 extract, because of the polarity of the sugar moiety. And we have both glycosidically bound aroma components in hops and glycosidically bound polyphenols. And in 2006, we published a paper reporting on the occurrence of glycosidically bound flavor components in hops, hop products, and beer. So we were the first to show their concentrations in various hop products. We did not discover these compounds. These compounds were discovered in the late 90s by the Miller Brewing Company in the United States. But what is useful and interesting regarding this compounds, this glycosidically bound aroma compounds, for example, Linoleal, which is known to be a contributor to hoppy aroma in beer, if it is present in a hop product in its glycosidically bound form and is transferred to the brewing process via the hop product, then it can be released from the sugar moiety during the brewing process. This is mainly done during fermentation, but also during aging there are processes releasing such compounds. And we not only have aroma compounds bound to sugars, but also polyphenols. And one example are the multifenols. Here you see on the left hand the glucose part, and on the right hand the multiphenol. And the multiphenols, we have different homologues, the co, N, and at homologues. So these are the same homologues as also present for the alpha and beta acids. And this is because these multiphenols are intermediates of the biosynthesis of this alpha and beta acids. And they are present in hops, and they can be transferred to the total resin extract. And another group is here. These are again polyphenols, and R1, R2 are different sugar moieties. So the camphorol 3 glucoside, here the R1 is a hydrogen, and the R2 is the glucose, and quercetin glucoside is very similar, but R1 is an OH group. But you can also have another sugar at the R2 place, for example, the rutinols. Then you have a rutinoside, and there is a range of various glycosides of these compounds, and these are flavonols bound to sugars. And they are especially interesting for the next point I would like to discuss with you, and these are the hard resins. And for a long time, the knowledge was more, or it was more believed that hard resins are oxidized compounds coming from the soft resin fraction. But this was completely revised And the fundamental study was published in 2015 by a group at the Technical University of Munich, Chair of Food and Chemistry, Molecular and Sensory Science. Professor Hofmann is the chair of this group, and Michael Dresel did the studies during his thesis. And I would like to cite his conclusion, or what is given in his abstract. After he has done all the studies on the sensomics analysis of the key bitter compounds in the hard resins, he concluded that for the first time now, based on liquid chromatography, MS, mass spectroscopy, quantitation of these taste compounds, he could find in Pilsner beer, and followed by taste re-engineering experiments, he could reveal the additive contribution of isoalpha acids and the identified hard resin components to be truly necessary and sufficient for constructing the authentic bitter percept of beer. So it's the combination of isoalpha acids and hard resin components that is necessary to get this authentic bitter percept. The authentic bitter percept coming from the hop cone. And these are some hard resin components he could identify in beer samples. And after he had identified them in the beer sample and also in the hard resin fraction of hops, he had the pure compounds, and he could determine the taste threshold concentrations. These are given here in the first column, and this is compared with their contents in a beer sample. And as already mentioned, we have in the hard resin fraction the prenyl flavonoids. Main component is xanthohumol. During wort boiling, xanthohumol is converted to isoxanthohumol. And you have another compound called desmethylxanthohumol. And you have glycosidically bound polyphenols like the quercetin and camphorol glucoside or the co-multifidol glucoside. So these are the main components. And if you have a look to the concentration in beer as compared to the bitter taste threshold, you see some of these compounds are not contained in beer. Some are contained, for example, isoxanthohumol, but the concentration is lower as compared to the taste threshold. And the same for the polyphenolic bound glycosides. You have also here for co-multifidol, a concentration which is below the bitter taste threshold, but it could happen that you have higher concentrations in beer as well. Then you have a direct contribution of this compound. But all together, these compounds are interacting with the same bitter receptors in the human body. And so they have an additive effect. And if you have a large number of compounds which are below their taste threshold, nevertheless, they can give a contribution by additive effects to the bitter taste. And actually, beside of these examples I'm showing here, 33 more prenyl flavonoids and polyphenol glycosides could be isolated by Dresel, and he could prove that they have a bitter taste. But these other compounds are, again, their concentrations are low in beer, and they only have a contribution to beer bitterness because of additive effects, but totally it's a number of 39 compounds. And the alternative proof of their taste impact was done by this re-engineering experiment, also described in this paper from 2015. Dresel had a zero beer, an unhopped zero beer. And the bitter intensity scale is here up to 3.5, and this has a bitter intensity of 1. And then he spiked the zero beer with isoalpha acids as contained in a typical Pilsner beer. He had a reference beer, and by addition of the alpha acid, isoalpha acids in a concentration as typically present in a Pilsner beer, he got a bitter intensity of more than 2. But after then adding to this beer with the isoalpha acids, in addition, all the 39 hard resin key bitter compounds, the bitter intensity increased. And actually, it was more or less identical to the Pilsner beer he used as a reference beer. And he detected all the concentrations, isoalpha acids and hard resin components in this beer and he spiked them in the concentration as present in the beer to the zero beer actually. And so this is the proof that the hard resins have a quantitative contribution to beer bitterness, and with regard to quality, this is what is also given in this paper. The zero beer plus the isoalpha acids plus all the hard resin key bitter compounds was described as beer-like, long-lasting and well-rounded without any specific off-taste. So the hard resin components also make a positive contribution not only to the bitter intensity, but also to the bitter quality of beer. And what is the fate of these hard resin compounds in the various hop products? This is also, Dresel gave some information, but in our laboratory we have developed a method on measuring all these compounds, the glycosidically bound polyphenols, and just recently I had an oral paper at the virtual World Brewing Congress last year, and we will publish a paper a paper in a journal will follow soon. And actually, what you can see, what Dresel could found out, and what we could confirm, is the xanthohumol and all the other flavonoids are transferred from hops to pellets, both types of pellets, and also to total resin extract, whereas CO2 extract doesn't contain them. And the multiphenol glucosides are also fully transferred to pellets. We have some losses from hops to total resin extract, but they are not present in CO2 extract. And with the glycosides of camphorol and quercetin, we have higher losses in total resin extract, but some of them are still present in total resin extract, whereas CO2 extract is free of it. And as I mentioned already in the beginning, there is a new process for CO2 extraction with higher pressure, and therefore, let's say the statement only pellets and total resin extract contain positive hard resins may be not longer true, because with 500 bar CO2 could extract some of these compounds, and this is already shown, or this was already published. There was a paper last year, Advances in Hop Extraction with Supercritical Carbon Dioxide. And here the differences between a CO2 extract produced at 280 to 300 bar and 500 bar is explained. So this is also what is given there in this paper. Substances can be extracted with CO2 at 500 bar, which are insoluble at 300 bar. The extract yield based on the quantity of pellets is almost 1% higher at 500 bar than at 300 bar. Besides containing more chlorophyll, we have already learned about this compound in the beginning, which makes the 500 bar extract greener. The 500 bar extracts are slightly richer in xanthohumol and contain more positive auxiliary bitter substances from the hops. And this is exactly the fraction of the hard resins. And so this 500 bar extraction moves the CO2 extracts more to the direction of the total resin extract, so the differences become minor. Now the next letter, the isoalpha acids. It's also a fact, and an interesting fact, that during production of total resin extract, a small part of the alpha acids is isomerized. And therefore, after its introduction, the total resin extract showed about 3 to 4% isoalpha acids. But in 1993, so about 10 years after introduction of this product, the extraction was modified to a more gentle process, and since then, less alpha acids are isomerized, and the total resin extract only shows about 1% isoalpha acids. And we have published this in 1994. All the actions we have taken to optimize and to make the process more gentle. And what is also important, that this isomerized portion has always to be considered in the dosage of total resin extract. Either you take the so-called total HPLC value, alpha acids and isoalpha acids, or the conductance bitter value, consisting of conductance value plus half of the isoalpha acids, because the other half is already considered in the conductance value. But because isoalpha acids make a bitter contribution in the beer, of course, you have to consider them in the dosage as well. And this brings me now to the next letter. And believe me, this was the most complicated for me, J. I was thinking over J. But then I reminded, soon after I have started at Hopsteiner in 1990, we had an anniversary, 10 years of alcohol extract. And so we have now 30 years later, we have another anniversary this year, another jubilee, we have now 40 years. So the letter J is now covered. Now we come to K, kettle addition. As usual for hop extracts, you add them at the beginning of wort boiling, usually gram alpha per hectoliter. But if you compare CO2 and ethanol extract, there is some interesting observation. I can't show it, or it's not possible to show it in a boiling wort, but it's shown here in boiling water, because 10 minutes after hop dosage to a boiling water, you see the following picture, whereas there is already a full suspension of the total resin extract. The CO2 extract seems to build globules of lipophilic materials. And this is because of the difference in polarity. The total resin extract is more polar. It contains all the polar hard resins, and therefore the solubility is better. It goes faster in solution. And this was also shown in 1993 in a paper in the Swiss journal Brauerei und Getränke-Rundschau in pilot scale, when you follow the isomerization of the alpha and to the isoalpha acids between CO2 extract and ethanol, total resin extract. These are the figures of 2 brews, mean values of 2 brews. So this is the line for the alpha acids in the CO2 extract. So you have the dosage was about 100 milligram per liter, and you have a steady decline, but still some residual alpha acids in the wort. And this is the line for the isoalpha acids. So alpha acids disappear and isoalpha acids appear during the process. And now the comparison to the ethanol extract, already from the beginning on, you have lower concentrations of alpha acids. In the end, you see also a faster isomerization rate, but in the end, you have very similar concentrations. So because you have a long boiling process, these disadvantages from the beginning, the CO2 extract has can be compensated. Nevertheless, in this paper I just mentioned, the conclusion was done that based on this semi-pilot brewing tests with ethanol and CO2 hop extracts, it became evident that alpha acids enter into solution slightly faster and isomerize more rapidly when using an ethanol extract. Yield of bitter substances is lower when using a CO2 extract. Depending on analytical method, the difference amounts to about 4 to 7% in the finished beer. And also contained in the conclusion is that this lower yield of CO2 extract can be mainly attributed to an insoluble hop residue observed in the whirlpool. This resinous material still contains 4.9% alpha acids and 6% isoalpha acids. But it may be assumed that on an industrial scale, the difference in yield between ethanol and CO2 extract will be lower. So this is the clear message. This is, let's say, the principle behind the different isomerization behavior. But if you have an efficient wort boiling system, there will be no differences or minor differences in the end. And also an important message from this paper is that all said ethanol and CO2 extracts yields beers that hardly differ from one another in an analytical and sensory terms. So this is also an important message. Now we come to the L. Linoleal is one of the volatile components in hops, and like other polar hop aroma compounds, terpenols, esters, ketones, and epoxide, it is almost fully recovered in the total resin extract. because they have rather high boiling points. Whereas myrcene is very low, has a very low boiling point, and like other monoterpenes, it's partly removed together with the extraction solvent, and we have losses of up to 50% for myrcene and other monoterpenes, but higher boiling sesquiterpenes like humulene and caryophyllene are better recovered, and they also show recovery rates of at least 90% in the total resin extract. So you have mainly losses of myrcene when you produce the total resin extract. NO, these are now nitrate and mycotoxins, or ochratoxin and other mycotoxins. Nitrate present in hops is extracted, but the main part is then transferred into tannin extract and not into total resin extract. This is because nitrate is a polar compound. It goes to the tannin extract. And the nitrate reduction actually is about 90% from hops to total resin extract. And this was published already in 1991 from our company. And with ochratoxin and other mycotoxins, it's very simple because hops and no type of hop products contains any mycotoxins. And we have made a publication, a report on this in 1999, and we compared various hop products, but there is no concern with regard to mycotoxins for hops. Now to the polyphenols, although I have already explained them to you before, I would like to give you still one overview. After hop extraction with alcohol, concentration 90%, followed by removal of the solvent and subsequent centrifugation, you get the tannin extract and the total resin extract. You get two phases. The polar tannin extract contains the water and all the polar hop ingredients. And with regard to polyphenols, these are the flavanol monomers, dimers, oligomers, and so on, called tannins. Whereas the total resin extract contains the essential oil, the soft resins and the hard resins, and the hard resins consists of polyphenols, the prenylflavonoids, the multiphenol glucosides, and the flavonol glycosides. So this again an important message that polyphenols are not fully in one fraction or in another. It depends on the type of polyphenol. Maybe another important information is that tannin extract can be finally mixed with the total resin extract to a so-called alpha standardized extract. So you have no alpha acids in the tannin extract, you have alpha acids in the total resin extract, and if you always want to have, for example, 30% alpha acids in your tin, you can do this mixing prior to filling. Quality. So this is another, of course, very important point. And the quality of the total resin extract was confirmed by various external brewing trials in the beginning when the product was introduced. And altogether, they show good beer quality resulting from total resin extract. And the studies were done in Weihenstephan at the chair of Professor Nazis, at the chair of Professor Donhauser at that time. Also in the Swiss journal Brauerei Rundschau, there were papers, and 1996 there was another Brauwelt paper, comparing then total resin extract and CO2 extract, and I will come back to this in a minute. But of course, after release, people wanted to know what is the quality resulting from this product, and the feedback was positive. And now what is the quality compared to CO2 extract? This is this Brauwelt article from 1996, and this was commercial brewing trials and not a semi-scale, pilot scale brewing trials. They were done at the Diebels brewery at that time, and it was a paper written by our group together with the Barthaus group. And the trials were actually done in the brewery, or the production was done in the brewery. And both total resin extract or CO2 extract was added at the beginning of wort boiling based on HPLC values. There was also a little pellet addition, and the extract addition was 5.7 gram alpha acids plus isoalpha acids in the case of total resin extract per hectoliter. The final beers then, and this is the message, showed that the analysis of bitter substances did not show any significant differences for any characteristic, and the yields are practically identical. So this is the confirmation of what was already discussed in the pilot scale paper. In practice, the yields are practically identical. And now with regard to quality, the tastings of the beer did not show any significant differences, both with regard to intensity and quality. So if you substitute total resin extract by CO2 extract or CO2 extract by total resin extract, no big differences are expected. And very recently, an interesting paper was presented at the EBC Congress 2019 in Antwerp. In the end, this poster was elected that to be the best poster of this Congress, and the studies were done at the Bitburg Brewery. And I give you the conclusion of this study, because in this study, CO2 ethanol extracts were also compared and mixed with pellet additions. And this study shows that non-isoalpha bitter compounds can influence bitter quality, and due to their different polarities, CO2 extract contains less phenolic compounds than ethanol extract. This is what we learned before. Pellet addition can partially compensate these differences and tends to have a positive effect on the harmony of the final beers. So in order to achieve the same positive effect in the CO2 as in the ethanol extract, more pellets have to be added to the CO2 extract apparently. And this is a nice confirmation regarding the contribution of the more polar hard resin components that are missing in CO2 extract but are present in total resin extract. It's a very, very interesting aspect which we know now. Residues of pesticide. I know, Frank, I'm a little bit off time. Okay. Relaxing was his sign. Also an important point. Here we have some active ingredients and the transfer rates to total resin extract green colored or CO2 extract yellow colored. And we have, and this table comes from a paper we had published in 2014. And you see two groups of compounds. Here you have the group of compounds with higher transfer rates in the total resin extract. And here is a group of compounds with higher transfer rates in the CO2 extract. You even have sometimes transfer rates higher than 100%, which is not possible, but actually it's because of analytical deviations, the analytical errors, because you compare the concentration in the extract with the concentration of the starting material. So if you have a full recovery, you can also have transfer rates. The number can be higher than 100%. But the picture clearly shows that the transfer rates of pesticide residues from hops to extract depend on polarity of the corresponding active ingredient. Some pesticides are better transferred to total resin extract and others to CO2 extract. And the whole picture may change in future if you have the 500 bar extraction, but I don't expect, and I think in this paper it was also discussed already, the recovery rates will not go up significantly because of the higher pressure. But of course, the trend will be to higher transfer rates then. The last letter, spent hops, very easy. These are the residues after hop extraction. They are pelletized and we can sell them as a feed material. Throughput of the plant may be also interesting. We have a rather high capacity, higher than in our CO2 plant, because here at Hopsteiner we run both total resin extract plant and CO2 plant. For the total resin extract plant, we have 2 tons of hops per hour, 48 tons per day in 3 shifts. And when we have a 5-day week, we have 240 tons. So that's a huge capacity. And also an important or interesting information, this Mainburg total resin extract plant has always been and still is the only one worldwide. So nobody else has built such a plant. Why? Maybe I come back to that in the next slide. Before coming to this, I would like to discuss viscosity, V, because the viscosities of total resin extract at 50 degrees and of CO2 extract at 40 degrees are comparable. So CO2 extract is less viscose because it has a less complex composition, and the hard resin components are missing. Maybe the variation at 500 bar is then higher in viscosity again. And V, water steam distillation, because this is actually the last step of our process. To fully remove alcohol at the end of the evaporation process, we do a water steam distillation. And this is necessary to remove all the alcohol. By regular distillation, you can't get rid of all the alcohol. You need a direct steam distillation. And this is done under vacuum at 60 degrees. And exactly this step then is responsible for the isomerization of the alpha acids during the processing. But as we have an acidic environment with all the alpha and beta acids, the pH is about 5.5, and this is very identical to the word pH, and so the identical reactions are happening during this process. And actually, this was the patented key process for the successful production of total resin extract, because this allowed then for the phase separation. And having and owning this patent is a good example, whether it's good or not, because it actually prevented other groups to build up an ethanol plant, an alcohol extraction plant, and so we remained the only one. Others developed the CO2 extraction, and so the CO2 extracts are more widespread worldwide today as compared to total resin extract. Now my last letter is X. I make it very, very fast. X stands for xanthohumol. I give you just a few milestones, but maybe we can skip this. People can read it on their own. I think maybe you have a short look on it. This is how all the research happened. It started in 1930, and actually now we have a safety confirmed, and clinical studies are going on. And the bottom line, until today, we have more than 500 publications reporting on the potential health promotion by xanthohumol. And what is very, very special about xanthohumol, that it has really a very broad range of health positive activities against several microorganisms. It's active, but also against DNA damage and cancer. So this is all I wanted to say to xanthohumol. But have in mind, during wort boiling, xanthohumol is converted to isoxanthohumol. So xanthohumol only is introduced to beer maybe by dry hopping. Last slide, conclusions. Also, the total resin extract was invented 40 years ago. New research and insights into its composition make it, according to my opinion, to our opinion, a rather modern type of extract, both with regard to brewing values. Think about the hard resins, but also with regard to the health aspects coming from xanthohumol, but also from other ingredients. And this is always my saying: if it wouldn't already exist, one should try to invent it today, this product, as the most natural hop extract. And as we learned from the studies I presented, because of this natural full spectrum bitterness, total resin extract is the most suitable type of hop extract to substitute pellet dosages, but you can also substitute CO2 extract, resulting in a similar beer. And I think this is a perfect message in the end. Take the risk and try the total resin extract. And now we come to the questions. So thank you for your attention.
Yes, Martin, thank you very much for this very interesting and very complete presentation about this fantastic product, Total Resin Extract. And it was good to see that you have certain ideas and certain comments regarding every letter from A to X.
The problem was the alphabet is very long, and so
yes.
for time also.
But what I find is very interesting as well is that regarding the slide where we have seen the iso formation in the kettle over the time, there was especially around the 60-minute boiling time, there were much better results, much higher utilization regarding the total resin extract compared to the CO2 extract. And with a look on the breweries today, they all try to reduce the impact of energy. They all try to boil shorter than 20, 30, 40 years ago. So they go to 60 minutes, they go backwards in direction to 40 minutes sometimes. And so we have seen that the total resin extract is very positive also in comparison, or especially in comparison with the CO2 extract. So ladies and gentlemen, let me say thank you again to my colleague, Dr. Martin Bienel. Have a look now on the questions, and I will read the questions and give these to Martin, the word to Martin again to answer.
And if we can't make them all, we can do it afterwards, of course.
Absolutely.
Yeah.
Martin, do you see any issues regarding the formation of isoalpha acids in the process of the total resin extract?
No, and this is why I explained at the end of the presentation. Maybe the question was before I had my slide on this water steam distillation, because I wanted to demonstrate, because actually it's during water steam distillation, a very similar process to wort boiling at a pH of 5.5 roundabout. So the surroundings of the environment is acidic because of alpha acids and beta acids. They are acids. They make the whole solution acidic. So you have a similar or identical conditions as during wort boiling, and therefore this conversion can be considered to be beer-like, and therefore I have not any concern about this isomerization happening. It even improves the utilization. However, then this was the problem, because not all the alpha acids are really converted to isoalpha acids. Only about 50% you can find as isoalpha acids. We also know it from the beer process. And so actually we could not consider the full isoalpha acids in our dosages. So it was underestimated always when you have a high ratio of isoalpha acids. And therefore this was also a motivation to make it more gentle, to try to reduce the isomerization.
Okay, thank you, Martin. Next question comes up here. Why do you produce not only total resin extract, but also CO2 extract?
Because we wanted to give the customer the choice which hop product to use. Here at this site, we started with ethanol, with total resin extract production, and only about 10-12 years ago we have decided on building up a CO2 extraction plant as well, because then it is the decision of the customer. It is not our goal, let's say, to convince, or we try to offer both. I think this is the right answer, Frank.
Yes. Yeah.
We want to offer both. And you have also pellets. You have type 90, type 45. And we produce both, and the brewer decides which product suits better to his process. And this is the same with the CO2 and ethanol extract. And I think it's even a benefit that the brewer has the choice, but you can make beers, good quality beers with all these hop products in the end.
Yes, absolutely right. Another question is about the dosage systems. If brewers switching from CO2 to total resin extract, is it possible to use the same dosage equipment?
Yes, definitely. But you have to be aware of the higher viscosity of ethanol extract. So if the difference is about 10 degrees if you compare the lines. So if you dose at the temperature of 40 degrees, you have to raise to 50 degrees for the total resin extract. If you dose at 35 degrees, maybe then 45 degrees is working for the total resin extract. But you have always to consider this difference. In the end, it could also depend. It's not a fixed difference. In the end, it depends on the hop variety, on the alpha content of the extract, maybe also on the crop year. But as a rough information, please consider this difference of 10 degrees.
Yes, and then coming to the varieties, as you mentioned, do you only produce total resin extract from bitter varieties, or do you also make extract from aroma varieties?
Yeah, we do both. We do bitter and aroma varieties. The ratio for bitter is higher because usually extracts are more produced from bitter varieties. But actually, with this information on the hard resins and their concentration, the relative concentration is higher in aroma hops, it would make definitely sense if you switch from a perlate tradition pellet to an extract, that you take then the total resin extract from this variety and not the CO2 extract, because for the CO2 extract you have no differentiation, or not this extent of differentiation in the product. So it's perfect. This is the perfect extraction solvent for aroma hops, I would say.
Yes, absolutely. I have one question here regarding the polyphenols. As we have seen, the polyphenols normally are separated from the total resin extract, but there's also the option to buy both in one product, in one container. And what is the impact by these polyphenols regarding bitterness, regarding mouthfulness, regarding astringency? Do you have any ideas about this?
Yeah, this is more the tannin fraction, and of course they contribute to mouthfeel. Some say it's more astringency than a smooth bitterness. But please have in mind, you have the same compounds also added if you use pellets. So in principle, it makes sense. But on the other hand, you have nitrate in this tannin fraction. You have part of the very polar pesticide residues. So with regard to a clean or residue free or an extract poor of residues, it makes more sense to use the total resin extract. And this tannin fraction is not very important, I would say. And today we can do the analysis and we do the weight per alpha acids. We can exactly weigh in 500 grams of alpha acids. So there is no need for standardization anymore because of these capabilities we have today. But in principle, you could use this extract as well. It comes from hops and goes through the same process.
Okay, and one last question from a colleague, very special question. Is it possible to make a partitioning with ethyl acetate to perform a kind of fractionation of the compounds of total resin extract?
So further processing, yeah, this is, for example, something that we do when we isolate xanthohumol from a total resin extract. We have procedures, and we even used in the beginning ethyl acetate because this is allowed in Germany for food production. So yeah, you can use another solvent if you want to further fractionate it. But we are not developing this products for the brewing industry, first of all. In the meantime, we have another process starting with the spent hops from CO2 extract, only using alcohol-water mixtures. But it's possible in principle to use this as a starting material, this fraction, for further isolating some compounds. Right.
Okay, thank you very much, Martin. I also got good feedback here. Great talk, Martin, from the people there on the screen. So again, also from my side, it was a great talk. And
so hopefully
it was not your last talk here on this hobby topic series that will go on further around the years. And we have learned a little bit about this product, Total Resin Extract, also in comparison with CO2 extract, that it's possible to switch from one extract to the other one. And there are some differences in between, especially regarding utilization in lower boiling time, and also regarding the spectrum of the bitter compounds, because its name says it, it's a total resin extract. Okay, let me say you welcome for today and that you are joining our webinar. And also thank you very much for the interesting questions that we got from your side. Now it's time to close the session for today, and I hope that you enjoyed our webinar. You will receive afterwards a short email that will give you a link to watch the recorded video of the today's session. And in addition, we would be happy if you give us a very short feedback directly after closing the session. And if you have any more questions regarding total resin extract, the utilization, and so on to Dr. Biendl, or regarding brewing related questions for me, please write it in an email and we will answer as soon as possible. Also on our website, under the section technical publications, there you can also find some papers regarding the topic of today. Some papers from the past were published all around, let me say, the last 20-30 years with information regarding total resin extract, or in the old days regarding ethanol extract. So the next webinar will be on Thursday, the 6th of May. Here at the same time, we will having a webinar with two people presenting. There's Dr. Matthias Hutzler from the Weihenstephan Research Center. He will be our guest speaker, together with our manager of technical support, Sandro Kokusa. And they will talk about the antimicrobial effects of hop components, of hop bitter components, on typical beer spoilage bacteria, and the results of an intense study that was performed last year and was also published last year. So until then, all the best for you, and please stay healthy. From my side, from Dr. Martin Biendel's side, farewell from Mainburg.